Signals and multidimensional functions appear throughout science and engineering. This video will cover continuous and discrete functions, giving examples, as well as going through one through to multiple dimensions of examples, up to 5 dimensions in fact. And also I'll be touching on the very key concept of basis functions. So to understand signals in the context of signals and systems, for example, we must understand what functions are. So functions can be from 1 through to multiple dimensions, and the number of dimensions is referring to how many independent variables there are in the function. You know, what does that function value depend on? How many variables? So to give a specific example there, we could have something like a mountain height h, depending on spatial position x, or the height of a stone being thrown into the air, varying with time t. So we've got some value of the function h, depending on one independent variable for the case of a 1D function. And the brackets here, whether they're square or whether they're round, round here indicates a continuous value of x. That means that this value h depends on the contents of that bracket. So we can consider continuous functions like the one I'm showing here, a function of time, where t again is a real value here, going from minus infinity to plus infinity, or we could consider discrete functions. But to build up to discrete functions, what I'm showing here first of all is the idea of sampling that continuous function at various points in time, and then we could arrive at a list of values, of function values at particular integer indices n or t or whatever we care to name them. So here I'm showing a discrete time function f of t, square brackets now to show that this value of t is now an integer, and so it's a discrete value, and then we get a continuous value f that depends on that discrete choice of time t. Also, it's worth pointing out that the actual function value itself could also be discretized or quantized. Nearly always, though, we'll assume the function value is continuous real value or a continuous complex value, but it could also be discretized, just like here I'm showing a discretization of time. So many types of notation are used, and here I'm showing a continuous function x of t. So t is here, that's the independent variable, and then we're getting some response x that depends on continuous time t. Here is an example of a discrete function where here in this diagram we're using an integer n as the independent variable for which we have a value x for each one of those values of n. Just to say that all kinds of different notation are possible, and so I'd really draw your attention to whether there are round brackets, which tends to mean a continuous independent variable, or if they're square brackets, which normally indicates that it's an integer or discrete index for the independent variable. So here's some examples now of 1D discrete functions. And so when I say discrete function, that nearly always is referring to the domain of the function, in other words, that independent variable. So a simple example here would be the stock market, where we have stock prices. We could call a price P as a function of time t. Now, price is itself actually quantized because in general you can't have any arbitrary price. It comes in sort of a discrete units, and then likewise time comes in discrete units as well. It could be day, it could be minute, it could be hour, and so p as a function of t in general is a discrete value as a function of a discrete value. But often we loosely write notation for functions. We might even just write loosely p as a function of time t, when strictly this should be interpreted as a continuous price as a function of a continuous time t. And so you have to be a bit flexible and understand in the context of the problem what kind of function you're dealing with. Okay, let's move on to 2D functions now. So a 2D function is one that gives a single value f, or here I'm showing h, as a function of now 2 independent variables. So 2D function means 2 independent variables. So I've got position x and position y here, and I'm getting a value h depending on the values of x and y, and that's going to give me a mountain height, for example. We could show it like this as a kind of a surface plot where we've got some kind of height, some kind of amplitude, varying with X and Y. Or indeed, I could show it as a grayscale image where I'm using white to denote these higher values here, and I'm using grays down for the lower values here. So this image is just reflective of the amplitudes of the function h, which of course depends on x and y. We could also show it in this kind of form here. And so we could be more succinct here and use a vector r, where r is an element of R2, r squared, which is just corresponding to a pair of real values. So that's just giving any continuous x and y position. So let's move on to discrete functions. So I've got a few examples here. So now we've got a height value as a function of discrete x and y positions. There was the continuous function that I had before. And now I'm showing a very crude discretization where we've got effectively an integer x, integer y, and then we've just got these particular values that I'm spelling out in red for this function. So that's now h as a function of r, where now r is a pair of integer values, x and y. Here's another example. This is a simulation of a PET scan of the brain. And so here's a continuous function. Here are two examples of discretizations of that function where we're using discrete values of x and y. And we're dealing with pixel values now to represent those integer indices of where the values are obtained. And we could plot these 2D functions, discrete functions, explicitly showing these kind of top hat functions for the pixels corresponding to the integer values of x and y. So this is with very high levels of discretization, and this is a more finely discretized image. And you can see all the discrete, effectively these are basis functions, but we'll get onto that later on. So MR is another example of giving 2D discrete functions where we've got x and y position indicating a pixel coordinate, and then we're getting some grayscale value f. For example, in MR, that's to do with net transverse magnetization is the source of the signal for an MR image. 3D functions, so going back to the example of positron emission tomography, we could consider a 3D image now, a radio tracer distribution throughout the brain, and again that's going to be reconstructed into a pixel or voxel grid. We're dealing with cubes rather than pixels. These are called voxels, volume elements, and so we've got integer indices of each one of those voxels, and then some radio tracer concentration value f as a function of x, y, and z. And here I'm just showing example 2D functions which are drawn from cross sections through that cube. So this is actually already a cross section, a transverse section through a cube that is the 3D image. This is transverse, this is coronal, this is sagittal. And indeed, we could even extract one-dimensional functions from these as well, just by taking a line profile through here, and then we get a function value f as a function of x, for example. So you can see with this 3D example, we automatically get a set of 2D functions and an even greater set of 1D functions. Another example of a 3D function would be a video or television or something like that, or even this this slideshow, if you like. We've got a grayscale x and y, so a grayscale value f as a function of x and y on this plane, this xy plane here. And then we've got a time axis going off in that direction there, showing those grayscale values change with time, and that could be a discrete time variable, for example. And so that's why I've got f as a function of x and y, grayscale value f, depending on spatial coordinates in 2D space, as well as depending on a time coordinate as well. Here's an explicit example of a moving image. This is a dynamic MR acquisition. And so we're seeing that we've got a function f of x and y, and it's clearly visibly changing with time as well. But as a note here, if we had color images, then what we'd be dealing with there would be, for example, using a 3-element vector, red, green, and blue, as the function value f. So we've been dealing with a scalar function value f, or indeed a complex value it could be. But in general, it could even be a vector value f, or a vector, I shouldn't say value, just a vector f, depending on, say, x, y, and t. That would be one option, or we could use the RGB red, green and blue as a further dimension to the data if we wanted to deal with it that way. In fact, in deep learning, for example, artificial intelligence, we often use multi-channel images, red, green and blue, as different channels, as if they're different dimensions of the image. Let's move on to 4D functions now. So now we've got 4 independent variables. So that's a 3D image as a function of time. We touched on that earlier for the 1D function case, but now we're actually going to exploit this and talk about it as a 4D function, because we've got a whole 3D volume for each time moment along this time axis. So that's why I'm showing X, Y and Z. X, Y and Z would correspond to the coordinate system for each one of these cubes. And then of course each one of these cubes is existing at a different moment in time, and this corresponds to the change in radio tracer concentration with time according to uptake, for example, of fluorodeoxyglucose in the brain, if that's what was of interest in this scan. Okay, let's get to 5D functions now to try and conceptualize what that would depict. So now again we've got a 3D image here in one of these cubes. That can change with time. So this could be some contrast agent in MR, it could be some radio tracer concentration in PET, and that's changing with time. So it's a 3D distribution changing with time. But to introduce yet another dimension, a 5th dimension, what we could do is consider what we call a gate position, which would correspond, for example, to the position of the diaphragm when the patient is breathing. And so what we can do is say when the diaphragm is at a particular position, then that corresponds to a particular value of the gate along this axis, and then for that instant in that position of the diaphragm, we could again get a 3D image which is also in general changing with time. And so with time we'd be populating different parts of the different gating positions, because as time progresses, so we cycle through all these various diaphragm positions, and so what we end up with, this axis here is giving us anatomical position, if you like, and this is time in terms of the difference in the radio tracer or contrast agent uptake, and then of course we've still got X, Y and Z describing a 3D distribution at any given moment in time and for any given position of the diaphragm, for example. So I'm showing that again explicitly with this MR example. So you can see the diaphragm here is just situated below the lungs there, and you should imagine that this grayscale image, the values could change with time, because here what we're seeing is the clear change in anatomical position of the lungs. And so that's how we get a grayscale value F depending on X, Y and Z, in other words in that volume, for a given moment in time and for a given position of the in the respiratory cycle in terms of the position of the diaphragm. Right, so you may be more familiar with functions that have these simple analytic expressions like shown on the slide here, but signals and images like the ones we've been looking at really are not that simple. And so what we need to do to capture the information, to represent the information in these rather complicated signals and images, is that we're going to need to use the concept of basis functions, where what we do is use simple building block functions summed together to form more general complicated functions or signals. And so that's going to be a really key concept in the study of signals and systems. And our core building blocks of interest in signals and systems are so-called delta functions as well as sinusoidal functions such as complex exponentials. So this is the concept then of basis functions. Well, I'm just showing a 1D function f of x here, and I'm showing that because we couldn't write that as, say, something like log of x or whatever, that's just going to be far too simple. Instead, what we can do is use this basis function b, and that could be a delta function or a sinusoidal function. I'll show you in a moment examples, which is going to have some kind of parameterization to control either the position or the shape of that basis function. And that basis function, you'll note, is a function of x. Okay, it's parameterized by k, but it's a function of x. And then what I do is just use a coefficient or an amplitude for each of these basis functions. You'll notice that there are in fact many of them because I'm summing over different parameterizations k of each of those basis functions. So I'll give you a concrete example in the next slide, but just to spell out this concept that we're adding together, if you like, these building block basis functions b of x, which have parameters k, and then we have particular coefficients for each of those building block functions. Sum them all together and that gives us our function. In the continuous domain, if now we're dealing with a continuous function f of x, now we have a continuous integral, so instead of that sigma, we now have a continuous integral dk, and our basis functions would be continuous, so it would be b of x, depending on some parameter k, and then we'd be using coefficients again. Now I've been calling k here a parameter, but we don't have to call it that. We could very much call that an independent variable, and that would be a very valid understanding. But I'm just trying to give different insights into what's going on. But here you can consider these as 2D functions and as 1D functions here. But because we're summing over one of the dimensions in these 2D functions here, that's why we end up with a 1D function on the left-hand side here. Notice how we sum over k. So k, when summed over, will not appear on the left-hand side. Here, when we integrate over k, on the left-hand side, we're only left with the independent variable x. So that's a really important sanity check when you write down integral equations or summations like the ones here. So as mentioned, those basis functions should be easy to understand, basic building blocks, the key point being that they're going to be easy to process and analyze when we deal with various systems, imaging devices, electronic circuits, whatever it might be that concerns the functions that we're putting into a system and the functions that we're measuring or reading out from a system. As mentioned here, there are infinitely many possible basis functions. The sky's the limit really, but in signals and systems we'll be touching on two main examples, and I'll quickly outline them here. So imagine we had some continuous function f of x here. Then what we're going to do is say that we could build that up using simple delta functions. These are these spike-like functions. I'm artificially spacing them out here, but they'd actually be infinitesimally close together to create a continuous function. But what you can see here is we can use different amplitudes of those functions and different shift positions. Okay, so that's what I'm trying to depict here, an amplitude of this delta function, and then here is a shift minus x prime. We'll get on to shifts later on in this video actually, just to clarify how that works. But so the shift position, if you like, is a bit like the parameter of that function. And then we're using an amplitude a, which we can view as a coefficient, which scales up or down that building block function. The point being, then we can sum together these building blocks with parameters which here correspond to the shift position, and using a particular amplitude of each of them in order to create the original function f of x, or in fact we use the terminology synthesize the original function f of x. We're synthesizing it from basis functions. The Fourier basis is another really key example. So here I'm showing another continuous function f of x. This is actually periodic, going from minus infinity to plus infinity. And the original function is this black sawtooth function. And what I'm doing is adding together building blocks, which I'm showing on the right hand side here, these sinusoidal functions. Instead of, remember in the earlier example, we were doing different shifts of these delta functions. With the sinusoidal building blocks, what we do instead is change the frequency of them. So the key parameter here is how many of these oscillations occur within some unit interval, and that's the frequency. So by adding together these building block functions of different frequencies and of different amplitudes, we can synthesize or recreate any particular function f of x. So that's what I'm showing here. These are the building blocks, sine and cosine, which can all be nicely wrapped up in a complex exponential. So this was Joseph Fourier. Sorry, I should have pointed out Paul Dirac, who was the one who devised the Dirac delta function. And we'll touch again on Dirac delta again here, as well as in another video. And Fourier, who came up with the Fourier basis. And in fact, I'll point you to other videos for comprehensive coverage of Fourier. Here I'm just touching on the concepts. So as I was saying then, we're recreating that function, this black line here, by adding together these blue basis functions, which in this case are actually, you can see they all look like sine waves actually. They're just negative sine waves. But in general, they'll just be complex exponentials with different amplitudes and, of course, different frequencies. And then that is how, and that's what I'm showing at the bottom here, this is actually, to give you an advanced notice, this is an inverse Fourier transform where we are synthesizing the original f of x by summing together these building blocks, these basis functions, which are the Fourier basis functions, complex exponentials. They're parameterized by frequency k. They depend on x, and then we have these coefficients or amplitudes f depending on the frequency k of the complex exponential. We sum them all up to arrive at a synthesis or reconstruction of the original continuous function. Right, I want to introduce another couple of functions here, well in fact one extra function because it leads on to the Dirac delta function, which is called the unit step function. So it's a very simple function indeed. Basically it's defined to be 0 for negative values of the independent variable and a value of 1 for positive values of the independent variable, and so we get this nice simple step. This is also known as the Heaviside step function, named after this English mathematician here. And there's variable definitions on how we define it for when the independent variable is equal to 0. You could use a value of 0.5, but let's not worry too much about that. Where we're going with this is to use this unit step function for finding another definition of the Dirac delta function. However, this step function will come in handy in various contexts in signals and systems where we're wanting to just look at just part of a signal. So let's consider then what that step function looks like. We could build it up in this kind of way here. Remember that problem at the origin? It seemed a bit awkward. It was 0 and then 1 and then not really defined at the origin. Well, what we could do instead is have a 0 function here, then a linear function. So this is just a straight line between 0 and this is capital delta here, going up to a value of 1, and then a straight line again holding that value of 1. So value of 0, value of 1, and then a linear function between 0 and delta. So we'll call that u subscript capital delta as a function of time t. So what I'm showing on the right hand side here is the derivative of that with respect to time. How does the function change with time? So here there is no change of the function with time, and so the derivative is 0. In this region here we can see the function is increasing with a constant gradient. It's constantly going up by a gradient, which is just given by this value here, the y value, 1, divided by, if you like, the x value, capital delta. So that means the gradient of this is clearly 1 over delta, and that's what I'm showing here, 1 over delta. That's the gradient of the function in that region. And then here, the function is no longer changing, so the gradient is again 0. So that's how we get this kind of top hat function, by taking the time derivative of this u subscript capital delta of t. Right, now what we can do is consider, well, what happens as this capital delta tends towards 0, because that's going to drive us towards that unit step function that we just saw on the previous slide. So what's going to happen? Well, first of all, I'm going to label this derivative as this function here. Okay, that's what I'm calling this pulse shape. As that delta goes to 0, this is going to get infinitesimally narrow, and 1 over delta is going to get infinitely high. And so what we end up with then is the familiar Dirac delta function. Now notice here, what's the area of this function here? Clearly it's delta times 1 over delta, which is going to equal 1. So the area, the integral, remains 1 at all times, irrespective of what we make capital delta to be. So therefore, as delta tends to 0 and we get this spike function, in other words, it becomes infinitely narrow and infinitely high, that's the delta function, then we still retain a unit integral. So that's why it's got a 1 there, indicating the integral of that function. Strictly speaking, it's not meant to be called a function, but you can treat it as a function in reality. That the integral of that function is equal to 1. And again, I'm showing Paul Dirac here, who was the one who devised this delta function. I should also say that there's a discrete version of this delta function whereby you could have square brackets here, and it would be 0 everywhere for all integers except an integer independent variable 0, where the value would be 1. Right, just to finish then, let's do transformations of the independent variable of 1D functions. It obviously generalizes to 2D and higher dimensional functions. So there I'm showing a discrete function x of n. So this is just some function value x changing with integer index n. And just to plot the function, what we're doing is considering n going from minus infinity all the way up to plus infinity, and then we're just looking at the function value. It's just defined as is on this slide. So let's see what happens then as we present an argument to the function. Here's the original function x of n. What we're interested in is saying what happens if we shift the independent variable. So n is the independent variable, and now what I'm plotting here is x of n with a shift minus n0. So n0 is a constant. Here n is an independent variable. n0 is a constant. Let's see what happens. Well, what happens if we just fix n0 to be, for example, a value of 10? Then to plot this function, what we do is we just, again, slide across this n axis here, just finding the value of n. So, for example, when we get to n equals 0 here, we'd plug n equals 0 in here, so that'd be x of 0 minus, if n0 is 10, then it'd be x of 0 minus 10, which means we look at this one, x at 0 minus 10, which is x of minus 10, is a value roughly here. And sure enough, that is what we plot there. Perhaps more instructive now is to consider the case when n is equal to n0. Okay, so if n is equal to n0, then the overall independent, the argument, if you like, for this function is then equal to 0, when it's just n0 minus n0. So we go to this one, plug in 0 as the argument here, and then we find that function value there, and that is exactly what we plot at n equals n0 on this axis. So the point I'm just laboring there is that when you see an independent variable minus some constant, it shifts the function to the right. This one should be obvious. This is time reversal or space reversal, depending on how you're defining your function. And it just says, well, if we now put a minus in front of that independent variable, then as we traverse positively along that axis, to get the function value, we have to traverse negatively in the original function. So that's why as we progress in this direction positively, we look up the function values from the original one by looking at the negative of the argument. And so that's why this plus, what is it, 1, 2, 3, 4, 5, 6, at n equals 6 here, we actually end up looking up x of minus 6 in the original function, which is that dip there. And that corresponds to a reflection in the in that kind of vertical axis about n equals 0, if you like. This is another final example I want to finish with, which is when we scale up or down the independent variable. So in this example, it's time scaling, but this applies spatially as well. If that's our original signal, x of t, continuous function defined between -2 and +2, then if we now have as the independent, as the argument of the function, if we now have 2 times t, so that's t is the independent variable, if we double it, that means as we progress along that time axis, so here, at this point here, t is equal to 1. So what happens is that we need to put a value of 1 in there, which means we need x evaluated at t equals 2 in the original function. And sure enough, that's why we get a 0 value here. If we were to go further along the time axis, for example, to t equals 2, then we'd have x of 4. And when I go to a value of 4 on the original function, it is 0, and that's exactly why I show a 0 in this plot. If we reduce the size of the time variable, for example, t divided by 2, then as I progress along this time axis, to find the function value in this plot, imagine I'm at 2 here, Then I do 2 divided by 2, which is 1, which means I've got to look up x of 1 in the original function, and you can see it's that kind of midpoint there, which is exactly what I plot here. As I progress to t equals 4, it's 4 divided by 2, which means I've got to look up x of 2 in the original function, which sure enough is where the function hits that time axis. And so when you use a greater than 1 scaling value for the independent variable, that results in a compression of your signal. And this is really important for when it comes to understanding frequency of cosines and sine exponential, complex exponential functions, because what that will do is compress those functions. So you get far more oscillations per unit interval. And conversely, if you scale them down, then that will stretch them out or dilate them outwards. So that's a really good way of visualizing these transformations of the independent variable. Okay, that's all I wanted to say for multidimensional functions and signals. I hope you found this useful. Thanks for listening.